All right. And it's really important that people come on time. Still seeing that people are trickling in as if it's some cafe. So please try to avoid that. One note is visible now.
Yes, sir.
Okay. So I can first take questions from either the first problem sheet or any of the lectures uploaded so far. Second problem sheet, any particular question you need to be discussed?
Sir,
Yes.
sir, I have a doubt from lecture 5 that when you have discussed the PV phase diagram. So can
Mm-hmm.
you please open that slide so that I can.
Tell me the page number.
So wait a minute, I will have to check the isothermal compression part. So above this, yes, this only, page 5.
Mm-hmm.
So in
Mm-hmm.
this, when we have considered the isothermal compression from the point D,
Mm-hmm.
and we have reached till point E. I did not understand it. Why did we go like this, the vertical till point B and then B prime? I mean, why not the isotherm would intersect this liquid plus vapor region, just like the rectangular hyperbolic thing. When we are looking at the temperature greater than the critical temperature, then it is a perfect isotherm. Then why in this region is it going like this? Why not
What do
the same
you
shape?
mean by a perfect isotherm?
I mean, like the curvature when the temperature is greater than the critical temperature. Why is this shape not like that? I mean, the temperatures at temperatures above the critical temperature, the isotherm is some different shape. Then why not
Uh-huh.
here? The
Yeah,
curve does not intersect it like that only. I did not understand.
because from point B up to point B prime,
Yes, the pressure
there
has
is
to be
a
constant.
P and T both are. So if you fix P, okay, so that is the coexistence region where a saturated liquid is getting converted into saturated vapor, and it is the property of pure species. Okay, if you add coexistence, there is only 1 degree of freedom. That
Yes,
means if you fix temperature, we are looking at isotherm, right? So I'm fixing temperature.
yes, sir.
Pressure will also have a fixed value. So therefore, for all points lying between B and B prime, including B and B prime, pressure is the same. And therefore it's a horizontal line. And in terms of why the shape is different, is because for all points between D and B,
Yes, sir.
the state is a subcooled liquid, and for all points between B prime up to whatever the end, the state is a superheated vapor. The two have different equations of state. So okay, so here what you're so I'm looking at two pure phase regions. I'm not looking right now between B and B prime. I'm looking to the left of B and to the right of B prime. To the left of B, I have subcooled liquid states. So the liquid equation of state would be valid there. And there, because you're fixing temperature, therefore a line will tell you the relationship between pressure and volume. Okay, and that line has a very different slope because liquid compressibilities are very different compared to vapor compressibility. So if you look on the right of B prime, you have superheated vapor states, and their compressibility is very different, and that is visible in the slope. The slope is much different from the liquid region. Okay, and in between, the Gibbs phase rule tells you that the specific volume of liquid and vapor has to be fixed, that we have discussed earlier. So in between, the only thing that is happening is the fraction of vapor is increasing, and therefore the combined specific volume V is changing. Okay, so the reason this shape is like this is because in the two phase region, V is not a Gibbs phase variable. It is a combination of two specific volumes, specific volume of liquid, specific volume of vapor. It's a weighted sum of those specific volumes.
Yes, sir. Got it.
Okay, so if you only look on the left, it's a regular curve. If you look to the right of B prime, it's a regular curve because it relates to single phase property.
Yes, sir.
Okay.
Yes.
Any other questions? Okay. Again, problem sheet one. Any query? Any questions? Problem sheet two. Any query? Any questions? Perfect. So you want me to talk to a wall? All right. So be it. Anyways, so we'll just discuss a few things, a few problem solving details. Okay. So this process is given to be isothermal compression, isothermal reversible compression. The first two are the important keywords. And they are asking you to calculate work because the process is reversible. I can use this expression. So here P refers to system pressure. Okay. So in general, for the expression of W, you will write P external. But when the process is reversible, P external is equal to system pressure, and therefore I have written PdV. Okay. The isothermal compressibility is given to you. Where C and B are constants dependent only on temperature. They're a function of temperature only. Okay, so they're not dependent on P or V. Okay, so from here, so essentially these are the two equations which I'm going to solve simultaneously. So given the form of this equation, from here I can extract PdV. Okay, so that's what you will do. You cancel out V, multiply both sides by P, and then take your dP on the other side. Okay, and all of this I'm doing at constant temperature. Okay, so because my process is isothermal, the partial derivatives here are being treated as, okay, ordinary derivatives. So this is what you will end up getting. From the expression for kappa, PdV, you can write in terms of P only. Okay, so now you can see the integration would be easy. And the other process detail which I'm using here is this is constant temperature. So now this you can plug into the expression for W and complete the calculation. Okay. 3.9 we can take a look at. So again, so for 3.4, because it was a single step process, I really didn't need to make the PV diagram. But here it's a multi-step process. It's always advisable to draw the PV diagram before you start to solve the problem. Okay. So point one is, let's say it's some pressure and temperature. And now you just go step by step. So from 1 to 2, they are saying the process is isothermal. And in the bracket, I am putting the quantities, the parameters that are known about that state point. Okay, state point 1, PT are known, state point 2, P and T are known. From 2 to 3, the process is isochoric. And the pressure has been specified at point 3. Then at 4, pressure is specified, and 3 to 4, you can see the process is isobaric. And then from 4 to 1, the process is given to be adiabatic. Okay. So now if I, and then they're asking you to do some calculations about internal energy change, heat work, etc. Okay. So I'm not going to do those calculations, but it's clear that calculations can be done if the state point is fully specified. So that is the key task here. So if my state points are fully specified, I can complete the calculation. So here you can see it's a pure species. I need to specify 2 variables at point 3 and 4. That information is lacking right now. Okay. So you can calculate V2 because at point 2, P and T are known. Then since from 2 to 3 of isochoric process, you can get the second state point variable at point 3. So do that. Then 4 to 1 is adiabatic, and you can see at point 4, temperature is not available. So you can calculate T4 in terms of data given at point 1 and pressure at 4. So from here, T4 is also known. So now all the state points are fully specified. So you can complete calculations. So let's us take example of step 1, 2. It is isothermal. Ideal gas is given. So from here, I can say internal energy change would be 0. And therefore, I get the relationship between Q and W. You can calculate one, you will get the other. Okay. And similarly, you can go about other aspects also. Okay, so as long as these are reversible, you can complete it. We'll discuss in chapter 5, 6, 7 that when processes deviate from reversibility, which is pretty much always the case, how to complete the calculations. Okay, but for now, if you assume reversible process, you can easily complete the calculation. So key thing was get the missing information. Once you do that, and one more thing which might come in handy is for a cyclic process, internal energy change is 0. So that might come in handy for calculating one of the Qs or Ws. Okay. Any questions on this? Problem 3.17, any inputs, any, maybe read through the problem statement now and tell me what you think. If someone speaks up in 2 minutes, I can discuss this problem. Otherwise, I will go to the next problem. Okay, problem 3.15, read through it and explain the process. Some volunteer to explain what is happening. So go through problem 3.15. I believe I did not include it in the problem sheet, but it's a nice problem. So read up 3.15 and try to understand first whether the process is steady state or unsteady state. There's too much silence. Everyone unmute yourself.
Yes, sir.
Everyone please unmute.
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay.
Yes, sir.
What do you want? If
Yes, sir.
no discussion is happening, then from my side, I can just put some figures for these problems, final answers for these problems, and don't hold this tutorial session. It's a waste of my time, at least. I don't know. Maybe it's run this way, it's a waste of your time also. But tutorials cannot be run like this. If there is nothing coming from student side, I cannot run the tutorials. No, keep yourself unmute. It's okay. If there is noise in the room, then you ask people to keep quiet or you can log out. Okay, so if you can't sit in a silent room while taking class, then don't take the class. Everyone be on unmute. Okay, so now if I'm asking you to read the problem statement while you are here, why can't you do that? Okay, it's too advantageous to be on mute. Huh?
Sir,
Please, if you are on mute, then you can leave the meeting room. Either be on unmute or leave the meeting room. Choice is yours. I can only request. If you cannot be on unmute, then you can leave the meeting room. Yes, Rida, you were trying to say something.
Hello. हाँ सर. हाँ. हाँ तो मम्मी को यही
yes,
करो.
sir. So, sir, I was saying just yes, sir. I was reading.
From wherever the noise is coming, I request those people to please leave the meeting room.
हाँ. अपना अपना अपना. ओके ये ऐसे इसे ओपन करना है तो क्या हुआ है अगर सिग्निफिकेंट मैटर को कभी आएगा डॉक्यूमेंट है या फिर ये नीचे है ये थोड़ी ना
Okay, thank you. Yes, Rida.
Yes, sir. Sir, I would. I am reading the questions as you are asking me to. But sir, actually at the moment, it is my mistake. I have not done the questions this time beforehand. So I am not able to participate that actively in this tutorial at the moment. So I would
Yep,
just like.
I can see that. So see from my side, if there is so much silence, right? I don't even know if the problem is that my internet connection has broken and I'm not even able to be heard. Anyways, okay. Unless and until see, you will not get the same problem in the exam. And if I take a bigger step in the sense that if you only do what I am doing in the tutorial, which is just hear me out, you will not gain anything from this course. Okay, problem solving skills, thinking about new problems, they help you beyond just the classroom. Okay, so unless and until you can synthesize the given information yourself, you are not learning the soft skills required for helping you beyond the class or beyond the exam. Okay, so unless and until you are spending energy in understanding new things, Those new things could be problems which you're doing in the class during exams, or maybe you are doing some other thing, maybe taking some training or whatever you are doing. Unless and until you are spending your time in problem solving in some way or other, you are not going to grow your soft skills at least. Okay, maybe you will score in the exams, especially with online exams. I guess it is not so easy, difficult to score well. But really, the bug doesn't stop there. Okay, so you have almost 2-3 years of your curriculum in front of you. My advice would be, please use that time wisely. Okay, at least don't sleep through or don't play video games. So do something meaningful with your time. All right. One thing which I will try from next discussion session as well as tutorial onwards would be ask you guys to subdivide yourself into maybe 20-30 teams, so groups of 4 or 5, and divide the problems amongst yourself. So if there are 10 problems and there are 10 teams, each team will be tasked to at least solve one problem. Okay, so that we can understand when in the tutorial or in the discussion, at least I can understand what mistakes you are committing, what problems you are solving while attempting these problems. Okay. So 3.17. Okay. A process is given. You can read at your own leisure. One side is empty. On other side, you have some gas. Okay, and this entire container is insulated, and the membrane rupture. So this membrane has ruptured, and they are asking you a few questions about what is happening in terms of work, temperature, etc., etc. Okay, so if you apply the first law here, you will be able to find out that in this first process, when rupture happens, so state 1 is when the membrane is not ruptured, state 2 when the membrane has ruptured. Since the entire thing is insulated, there are no moving parts, no compression happening, the vessel is rigid. So I'm taking my system here as the entire thing, including the empty space. If you take your system as part of the vessel, the problem will be very difficult to solve. So I take my system as the entire vessel. And if I take that as my system, so the application of first law would be dependent on how you're taking your system. My system is the red dash line. With that choice of system, there is no exchange of work with surroundings. There is no exchange of heat with surroundings. Therefore, Q and W is 0. Therefore, by first law, delta U is 0. Okay. Since it's an ideal gas, I can further say no change in temperature. So T2 would be equal to T1 equal to 100 degrees Celsius. Okay. So free expansion process, no temperature change because of whatever is given. Okay. So whatever your intuition tells you does not matter. We have used our equations. My intuition might fail myself. So here I might think because expansion is happening, temperature must have reduced. But they are showing it mathematically, it's not the case. Okay. And then they are asking you construct a process by which you can come back to the initial pressure, temperature, and initial volume also. Okay. So that I leave to you. So part 2. Construct a process to reach the initial state. For that, you will first need to ask you which variable has changed and which has not changed. And accordingly, you will be able to devise a process to take the system back to the initial state. Okay. And here they're not talking about the empty part. So the initial state now only refers to the part where gas was. So whatever gas was here, temperature I have proven has not changed, but maybe the pressure has changed. So the pressure has changed, then the process must be able to reverse the change in pressure. Okay. Any question?
No, sir.
3.15. So it deals with the filling of gas tanks. which is a very routine industrial operation. So typically what you will have is a compressed air line, a valve. So by using this valve, you can control the flow of gas or air into a vessel. So this is the system given, and I believe they are telling you there is some heat exchange with the surroundings. So the vessel is not insulated. So there is some heat exchange with the surroundings. The gas here, so rather than saying air, maybe I could have said gas. Anyways, the gas given here is nitrogen. And the pressure and temperature I'm representing by P prime T prime, which is the pressure temperature maintained for the compressed gas. So whatever nitrogen supply I am having, that supply is at a fixed pressure and temperature. Okay. So I'll first complete the details, as per the details given in this problem, I will finish it out. And then we'll discuss a more practical scenario of the same thing. Okay. So the idea here is I want to fill nitrogen cylinders. Okay. So that is essentially what we want to do. I want to fill nitrogen cylinders. So let us see how it will be relevant. So again, the first task is choice of your control volume. So by choosing this dashed thing as my control volume, or actually I should take it across the wall. Sorry. So I take it across the wall. The reason I'm taking it across the wall is because I know within the compressed line, as per the given statement, pressure and temperature are not changing. So my flow stream is entering at a fixed value, and that fixed value of pressure and temperature is known to me. So the state of the flow stream is known to me before the valve, not after the valve. Therefore, I'm taking my control volume by including the valve within the control volume. Okay. So looking at the problem statement, there is one flow stream coming in, no flow stream going out, no moving parts. So work rate is 0, and there is some heat exchange with the surroundings. Okay. Here clearly the change in kinetic energy will not be equal to 0 because there is only one flow stream coming in. So something is coming in, but nothing is going out. So definitely this is not 0. But even here, you can ignore this term. Okay. But if you're not satisfied, you can complete the calculation and see if this term is significant. Okay. And you will indeed check, see that it is not significant. I can easily say change in potential energy to be 0 because I can take the datum. There's only one flow stream. So I can take the datum to be at the level of the flow stream. So potential energy change will be identically equal to 0. So put all of this in your general energy balance. The system in this case is not at steady state clearly. So the rate of change of energy of the tank. The second term corresponds to the compressed flow stream. And the last term on the right hand side is the heat exchange with the surroundings. So this is the working equation that I need to solve. And now you can clearly see some integration is required. Okay, so I can take n naught prime to be a constant, which is not fully correct. Why it might not be fully correct? As you fill this vessel, the pressure temperature conditions inside the vessel are changing. So that means across the wall, delta P is changing. If the delta P across the valve is changing, the flow rate might not be constant. Okay. However, if the difference between the compressed airline pressure and the vessel pressure is very large, then to a good approximation, you can still assume flow rate to be constant. Okay. So that's what we are doing here. H prime corresponds to properties of the compressed airline because it's a pure species. 2 degrees of freedom, pressure, temperature are fixed. Therefore, H prime is definitely a constant for the entire process. Okay. So given these two bits of information, I do an integration. So change in energy of the tank is your first term. Change in the moles inside the tank is the second term. H prime times the integral of N naught prime dt is just the total change in moles inside the tank. And integral of Q naught gives you total Q. Okay. Now what you can see here is both U and H are present. However, whatever expressions we have so far learned, they give me either delta U or delta H. Okay. Anyways, absolute quantities I cannot get. So H prime corresponds to absolute enthalpy. U corresponds to absolute internal energy. In thermodynamics, I do not have access to absolute quantities. I can only talk about change in a quantity. Okay. So if you expand this summation a little bit, so let us do that. The first term is, so here state 1 is the state of the this fluid, in this case that is gas inside the tank before the process starts. State 2 is the state process is finished, and the process is filling of a gas cylinder. So here if you see, even if I take, let's say, N2 out, I will get U2 minus H prime, which I don't know how to calculate. So either I convert U to H or I convert H to U, either way. Okay, so let us do the conversion of U to H. Similarly, N1 U1 you can write down as, and now you can see you will get one term as H2 minus H prime. So if you put this in here, one of the terms would be H2 minus H prime, which you can write in terms of Cp delta T. Cp is given to be constant. Similarly, the other term will be H1 minus H prime. Again, you can write down that in terms of Cp delta T because Cp is constant. Okay, so once you put all of this, you would see that Q is the only unknown. Okay, now that is slightly hypothetical. The reason is nitrogen, typically the way you are filling nitrogen cylinders, nitrogen is not at ideal gas like condition. So here, whatever data you have been given in this problem statement, they are saying that pressure and temperature conditions are such that nitrogen can be modeled as an ideal gas. Okay, so of course it made the calculation easy, but it took the problem away from practicality. So we will kind of revisit this problem. So from a relevance perspective, we have not fully trained ourselves. So we'll need to wait till chapter 6, where you will learn how to calculate these property changes for real gases. As well as you'll be able to learn how to account for these changes during phase change. Okay, so for example, if I want to fill a liquid gas cylinder, liquefied natural gas, liquefied petroleum gas, okay, CNG, compressed natural gas, LPG, liquefied petroleum gas, so on and so forth, liquid nitrogen cylinder, liquid helium cylinder. So you can see all of these, the way they would be filled would be, you would have a compressed gas, high pressure gas, and while filling, you will ensure the conditions are such that phase change also happens. Okay, So many times what is happening is a high pressure gas is being used. The conditions would be such that the ideal gas approximation is not going to be valid. And then the vessel in which you are filling it, so whatever cylinder you are filling it up with, the state could be liquid, high pressure gas again, or even supercritical fluid. So again, these conditions are such that the ideal gas approximation is not valid. So that is a more realistic problem. And that problem you would be able to solve once we get to chapter 6. So there's one problem which is essentially asking you to do this. Okay. These are state points where you will get big deviation from ideal gas behavior. However, the second law will not change. You will still get a similar working equation, but your calculation methodology will change. Okay. And there, let's say the question I might ask, let's say design question I will ask is problem. Relationship between mass in cylinder and the PT conditions in cylinder. Okay, it will be very difficult to measure the mass while you are filling the cylinder. So indirectly, put the pressure temperature conditions inside the cylinder. You put a gauge inside, even pressure might be sufficient. Just pressure might be sufficient. So if you can measure just one variable, let's say pressure in the cylinder, can you tell how much mass has been put inside the cylinder? So let's say that is my design question. And the answer is yes, you will be able to find out, given a pressure, what is the mass of gas you have put inside the cylinder. Okay, so this will attempt in chapter 6. Any query on this problem?
No, sir.
So now the problem, I don't remember problem number, either 10 or something else close to 10. It is asking you to calculate specific volume of steam using various different means. So I'm going to give you the answer so that you can check your calculations. And of course, P and T are given. So pressure is 68 bar. Temperature is 300 degrees Celsius. So this is the given condition as these conditions. Again, I don't expect ideal gas to be accurate. We'll do the calculation and check that. Okay. So this is what you get from ideal gas. If you use the van der Waals equation of state, 6.03. Redlich-Kwong equation of state, 5.81. And if I use steam tables, which are for superheated steam, saturated water are the most accurate answers. Okay, so steam tables are the most accurate answers concerning superheated steam, saturated water. So from steam tables, I get this value. So you can see even ideal gas was not too shabby. It was not too bad. But clearly there is a difference. Okay. And at industrial scale, 7 versus 5.5 is a significant difference where you will say that, okay, I am doing bad. Okay, so roughly you're getting 20% error, which is more than what is typically acceptable. All right. So now in terms of how to use steam tables. So this is something which is going to be required because a lot of problems which are given here are given for water And the reason being that is one fluid for which accurate information on PVT data is available. Okay, so that is why a lot of problems are given with water as a working fluid. So broadly, the steam tables are divided. If you look at the appendix in your book, appendix E, I believe, or F, one of those, you have steam tables in those appendices. There is one which concerns superheated steam. So that means temperature is above the saturation temperature. And the other which contains data on saturated steam as well as saturated liquid. So this other one contains data on both. Okay. And what information is contained in steam tables? Enthalpy, entropy, internal energy, specific volume. So these are the 4 bits of information which are contained in the steam table. And all of those, I believe they are putting the data in terms of per unit mass. So all of these quantities are listed in terms of specific values, specific enthalpy, specific entropy, specific internal energy, and specific volume. Okay, so these are the values which are given. Of course, you can have infinitely many combinations of pressure and temperature, but you have a limited space. Okay, so what is done there is, let's say I'm looking at the way this table is structured. So T is going in the horizontal direction, P is going in the vertical direction. Let's say the pressure is in bars. So the temperature might be with the closer spacing. And the reason is with temperature, I expect larger variations. Okay. So let's say this is the form in which data is given. So now you will see some columns would be empty. The reason some columns are empty is because, for example, these states would correspond to subcooled liquid states, and subcooled liquid data is not available in steam tables. So these might be empty. Okay. So we'll need to wait till I see Tsat. Okay, so I don't know what is Tsat at 10 bar, but whatever is the Tsat at 10 bar, onwards of that, you will see data being populated in the steam tables. Okay. So now if I give you a condition which is P equal to 12 bar, and let's say high enough temperature, let's say 500 degrees Celsius. So since the data is available at 10 and 15, you will do a linear interpolation between these 2 points. So between 10 and 15, you will do a linear interpolation to get the required value. Okay, so the required value could be for V, H, S, or U. All right. So any of those values, you will do a linear interpolation between these 2 points to calculate the value. And that's what was done here also. Okay, this exact state point, 68 bar and 300 degrees Celsius is not available. So therefore, I have done a linear interpolation between these 2 points. So that is how you can use a steam table. Any questions, queries? Okay. So last thing which I want to take up today is again one of the homework problems, equation of state decision tree, so to say. So that is how to decide which equation of state to use. So some hints have been given in the lecture class also, but let us try to summarize those details. So let's say the fluid of interest is a real gas. So for real gases, pure real gases, what are my options? Okay. So the ideal gas equation of state, the requirement would be high temperature, low pressure. It can be quantified a little bit, especially for temperature. You need to be above the so-called boil temperature. So TB is the boil temperature. For different species, the estimate of boil temperature is available. And if the temperature is above the boil temperature, and the boil temperature is the temperature at which the second variable is zero. So if you are at a temperature where second variable is zero, you can essentially say that I am at a high enough temperature that interatomic interactions are not relevant or not significant. Okay. So that on the temperature side, that is the condition. For the pressure side, the condition is expressed in terms of density. So V needs to be above some what I should use some cutoff value, let's say. So as long as V is high enough, what is high, what is not high? Okay, but there are rules of thumb available in terms of what is the density at which you can use the ideal gas equation of state. And of course, if you want to be very sure, then you use some other more accurate equation of state at the given conditions and check whether the ideal gas estimate was correct or not, just the way we did right now. Okay. Next is your cubic equations of state. So of course, the first requirement is parameters must be available. So whether the parameters are available or not, that is the first requirement. Now, one of the more accurate ones is the so-called extended variable equation of state given by Benedict, I believe, Weber and Rubin. This is especially good for hydrocarbons. So the oil and natural gas industry uses this particular equation of state a lot because this is especially good for hydrocarbons. Okay. In particular, when we want to do vapor liquid equilibria calculations. So when you want to do vapor liquid equilibria calculations, you need, so cubic equation of state, if you go back to the lectures, any cubic equation of state allows VLE calculations. What is VLE calculation? Calculate P set at a given temperature, calculate the saturated volume of liquid and vapor phase. That is what I mean by VLE calculation. Okay. So for oil and natural gas industry, this is a very important calculation. And cubic equation of state can do that calculation. Any cubic EOS can do that calculation. However, some are very good. Okay, so one of them is Bandit, Webb, Rubin. Another one which is very good for VLE calculations is the Peng Robinson equation of state. So these two are very good for VLE, and lot of papers, if you see VLE calculations being done for light hydrocarbons, you will see Peng Robinson or Benedict Webb Rubin equation of state. Okay, so those are the equations which are available. Besides these equations, we have correlations. These are your so-called analytical equations. Other is your correlations. And again, your correlations are in two forms. One correlation is in form of equation, which is the Pitzer second visual correlation. And the other correlations are in terms of tables, the less Kessler correlations. Okay, so now both of these are actually related to each other. So the validity is actually similar, except for the PT range. So the kind of species for which either the Pitzer second virial or the less Kessler is valid are apolar or weakly polar species. So oxygen nitrogen, CO2 comes in the weakly polar category, ammonia comes in the weakly polar category. For all of these, Les Kessler, Pitzer second virial are okay. For strongly polar species, for example, water, not so good. Okay, so that is in terms of species. In terms of PT range, a figure is given. So Les Kessler, now we need a separation between the two. So Les Kessler are applicable over a very wide pressure temperature range. On the lower side, up to saturation conditions. On the upper side, very close to critical point. If I start approaching pressures which are very close to critical point, PC, I will not use Les Kessler either. There are some very specific relationships available if you want to model fluid behavior near the critical point. But as long as I'm away from critical point and I'm looking at apolar, weakly polar species, Les Kessler are very good for pretty much the entire vapor region. Okay. Pitzer second virial, range is smaller, and that range in terms of PR/TR values is given in the book. So there is a figure in the book which shows kind of a contour diagram which gives you for each TR the PR up to which the second virial can be used. And the attraction of Pitzer second, if let's say Pitzer second virial, we are saying they are based on Les Kessler or they are less accurate than Les Kessler. Why do I use Pitzer second virial at all? The only reason is Pitzer second virial are in terms of equations, whereas Les Kessler are in terms of tables. So they are somewhat easier to use compared to Les Kessler. So if your conditions are such that you will not go to very high pressures, which are beyond the validity of Pitzer second virial, you can use Pitzer second virial and get answers which are of comparable accuracy as to Les Kessler. Okay, so of course this is not complete. There is a lot still which needs to be learned in terms of which equation of state to use, but that is beyond what we are going to discuss in this course. Okay, if I change the species, for example, if I say supercritical CO2, none of the things which I put here are valid, but supercritical CO2 is a very important industrial fluid. Okay, similarly, nitrogen for cryogenic applications. Whatever I have put here is not valid. Okay, so for that, it's kind of horses for courses. So depending on the exact species, exact PT condition, if you are interested in accuracy, very specific relationships are available, especially for industrially important fluids. Okay. So that's all. If there is any query, you can ask. So this ends the session and completes the discussion on the problem sheet 2.